Hi everyone, so here we are with the second video for this week, second and last. And this one's about the derivative of function, the definition, and some of the basic rules. First of all, we're going to be talking about tangent lines and the slope or gradient of a curve. So let's go to the next slide, and I'm going to show you something here really quick. Now, if you recall from the last video, I talked a little bit about a 17th century problem, which was to find a way to find an instantaneous velocity. It's very easy to find an average velocity, but finding an instantaneous velocity at the time had not been really solved. And a French mathematician, Pierre de Fermat, who was really a lawyer and a guy involved in the law, a judge and all that. But during his spare time, he loved doing math as an entertainment, as a hobby. He was the one that came up with this first. And in this slide, you're going to see an illustration of how he solved the problem of finding the gradient of a tangent line, which would give you the instantaneous velocity of something or an object at that given point. So if you look at this first graph on the top left, he thought of it this way. Normally we would call this point here x1, right? And this one would be x2. So he thought of h as the distance between x1 and x2, right? So in terms of h, we could say that if we don't call this point to the left x1 and just instead call it x, then we can call this other point x plus h, right, which is the distance between the 2 points, x plus h. Then that means that this coordinate here would be x comma f of x, and this other coordinate here would be x plus h comma f of x plus h. And also this distance here, this difference here, would be f of x plus h minus f of x, right? The difference in y. This is the difference in y, and h is the difference in x. So what he proposed was, let's make h smaller and smaller, and that's what you see in these successive graphs. Here h is a smaller distance. Here again, h is a smaller distance. And in the third graph, h is basically almost zero. It can't be zero, otherwise we could not apply the slope formula, which is really what is intended here. And so what's going on in this case? So what would be the slope of this line, right? Or actually, no, that would be the wrong slope, because this is the slope right here. The slope of that line at that point. And in the last video, I told you guys that that would be the same as talking about the limit as h approaches 0 of the difference in y, which is f of x plus h, minus f of x, difference in y, over difference in x, which is just that value h, as it approaches 0. So this would give us the instantaneous velocity or the slope of the line, of the tangent line, at that given point. So what we just saw before leads to this, right? Which is the definition of a derivative. So it says that the slope of the curve y equals f of x at the point x comma f of x is equal to the slope of its tangent line, and is given by this formula, right? Notice that it's the same formula. The limit as h approaches 0 of f of x plus h minus f of x over h, provided this limit exists. Remember that we can test limits by approaching the x value from the right and the left. And there are cases, of course, where you cannot do this because there's no limit. That's a differentiability issue. And we will see cases where lines are, or points of lines where they are not differentiable. It cannot be, there can be no derivative at that point. So here we are with example 12.5, and they say find a rule for the slopes of the tangent lines to the graph of f x squared plus 1. Use this rule to find the exact slope of the curve at the point where x equals 0 and at the point where x equals 1. So just so we understand what they're asking us to do, what they're saying is use the derivative rule to find the general rule for any derivative of this function at any point. So if we graph or sketch actually x squared plus 1, as you guys know, it looks something like this, right? So what they're asking us to do is to find the derivative of f, and it's symbolized with this apostrophe here, the derivative of f. And the derivative of f, what it's going to do is that it's going to tell us what the gradient of a tangent line will be at any point of the graph. So whether it's there, or whether it's here, or anywhere, right? So that's what we're going to do next. Now remember that the definition of a derivative, and we can say that the derivative of a function is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So in this specific case, it's going to be what? Well, it's going to be the limit as h approaches 0 of f of x plus h. So what's f of x plus h? F of x plus h is plugging x plus h in f of x, right? So that's going to be x plus h squared plus 1 minus f of x. So f of x is just f of x, x squared plus 1. And this over h. So now what you have to do is just manipulate this algebraically and get to a limit or that won't become undefined, and therefore we're going to get the function, or that's going to be a rule for all the slopes of the tangent lines to this graph. So notice that we can grab this expression and expand it. Let's do that. So limit as h approaches 0, and this would become x squared plus 2xh plus h squared plus 1, and that would be minus x squared minus 1, right? And all of this over h. Now notice that x squared minus x squared is 0, 1 minus 1 is 0, so we're left with only this, okay? And we can simplify this then, because we can factor out the h. So that means that limit as h approaches 0 of h times 2x plus h over h. So this will cancel out, and we're left with this only. So now we can plug in 0, and notice that what we're going to get is 2x. So 2 times x is the general rule that will give us the slopes of the tangent lines to the graph of f of x, or x squared plus 1. In other words, 2x is the derivative of x squared plus 1. So now we can answer the questions. So what would be the exact slope at x equals 0? At x equals 0, the slope would be 2 times 0, 0. At x equals 1, the slope would be 2 times 1, 2. Very well, so in the previous example, we saw that f of x equals x squared plus 1, which has a graph that looks more or less like this, where this would be 1 here, we found a general rule to find the slope of the tangent lines at any given point, and we saw that the derivative of x was 2x. Graphically, what this means is that, for example, at 0, remember that at 0, the slope would be 2 times 0, so 0. That means that at point 0, the slope of the tangent line would be 0. And we saw that at 1, the slope would be 2. So that means that at point 1, you have a slope that is equal to 2. So to generalize, we can say that the derivative f apostrophe x at the point x in the domain of f is the slope of gradient of the graph of x comma f of x, and is given by, well, this formula that we've been using, provided that the limit exists. If the derivative exists at each point of the domain of f, then we say that if f is smooth function. The process of finding the derivative is called differentiation. And then the derivative is actually a formula for the instantaneous rate of change of y with respect to x. So in example 12.6, they say differentiating from first principles, that means using the rule we just saw, find the derivative of f of x equals x cubed. So remember that the derivative of f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And in this case, it's going to translate as the limit as h approaches 0 of x plus h cubed minus f of x, so that's just x cubed, over h. And then this would equal the limit, don't forget to write this every time, as h approaches 0, of the expansion of x plus h cubed. And from binomial expansion, we know that that's going to be x cubed plus 3x squared h plus 3x h squared plus h cubed, and let's not forget minus x cubed. And all of this over h. So notice that here we can cancel out x cubed, and we're left with an expression that has a common factor, which is h. So we can rewrite this as, again, limit as x approaches 0 of h times 3x squared plus 3xh plus h squared. And this over h. So now we can finally cancel this bottom h, which is the one that makes it undefined. And we can finally plug in 0 for h, not for x, guys, for h. So let's plug in 0 for h, and what do we get? Well, this would cancel out, this would cancel out. So we're left with 3x squared. Therefore, the derivative of f of x is 3x squared. Very well, so here we are on example 12.7. And again, from first principles, find a derivative of y given that y equals 3x squared plus 2x. So again, this is applying the same principle. So this would be the limit as h approaches 0 of f of x plus h minus f of x over h. So we're doing a first. And then in that case, it would be, again, limit as h approaches 0 of 3 times x plus h squared plus 2 times x plus h minus f of x. So that would be just 3x squared plus 2x. And all of this over h. And then we could say that then the limit of the function as h approaches 0 is going to be 3 times x squared plus 2xh plus h squared plus 2x plus 2h minus 3x squared minus 2x. And all of this over h. Let's multiply this by 3 now that we're here, so we have enough room to finish this. So 3 times, let's do this here, 3 times 3x squared, 3 times x squared is 3x squared is what I mean to say. So 3x squared. This would be then 6xh. So let's write that there. And this here would be 3 times h squared. So plus 3 times h squared. And obviously we have to get rid of this 3 here. Okay, so that's what that expression would be. And I'm doing this to be able to simplify this. So 3x squared minus 3x squared, this will go. 2x minus 2x will also go. And then notice that we're going to be left with expressions that have a common factor h, right? So let's rewrite this down here. So this would equal the limit as h approaches 0. And let's write this as h times 6x plus 3h plus 2 plus 2, yeah, that would be it. And all of this over h. So h and the denominator would be canceled out. Now we can plug in 0 for h, and we're going to get that the derivative of y is going to equal 6x plus 2. Okay, now I realize that I'm not going to do b because it's the same as exercise 10 from the last practice. So I'll leave this one for you guys to do. Okay, so on the next slide, we have some of the rules, more general rules and a quicker way to do derivatives. So the first one is a constant rule, which says that the derivative of a constant equals 0. That means that if you have that f of x equals 2, then the derivative of that is 0. The next one is the power rule, and this one says that the derivative, if you have a function that is f of x equals x to the n, then the derivative of that would simply equal n times x to the power of n minus 1. What that means is, okay, or as an example, maybe it would be clearer if we have an example. If we have f of x is equal to, say, something like x squared plus 1, then the derivative of this would equal 2 times x to the power of 1, right? Because we send this to multiply and we subtract 1 from here. And because this is a constant, the derivative of that would be 0. And this is a direct reference to the sum and difference rule, that if you're doing a derivative of, say, a polynomial, which you can also see as the sum of several functions, you can do them individually and it'll be the same thing. So basically what I'm doing here is that I'm doing the derivative of x squared and then doing the derivative of 1. Notice that there's also a constant multiple rule, and that just means that if you have a constant, then you do the derivative and then just multiply it by the constant in the end. What would be an example of the constant multiple rule? Let's suppose we have f of x is equal to 3x to the 3. Then what they're saying is that we could do the derivative as equal to 3 times the differentiation or derivative of x cubed, and then this would equal 3 times 3x squared, and that is 9x squared. Now we could have done that, of course, in one step here, just by sending this to multiply and then subtracting 1 from the exponent. So very well, here we are on example 12.8, and it says for each function, 1, find the derivative using the basic differentiation rules, and 2, find the slope of the graph of the function at the indicated points. So let's start with A, and it's f of x is equal to 3 square root of x minus 6, and they want us to find the slope at the points 4, 0 and 9, 3. Okay, so the first thing to do here is identify the exponents of x. So notice that we can rewrite this as 3 times x to the power of 1/2 minus 6. Then the derivative, using the power rule, would then be equal to 3 times 1/2 times x to the power of negative 1/2, because I'm subtracting 1 from 1/2, right? And this is the minus 6. Derivative of that would be just 0. So then this would equal 3/2 x to the negative 1/2, or what is the same, 3 over 2 square root of x. Then they want us to find the slope at 4, 0. So notice that here we're only going to be interested in the x coordinate, right? Because it's going to be plug in the derivative, plug in 4 in the derivative, and the derivative gives me the slope at that point. So this would then equal 3 over 2 times square root of 4, and this obviously will equal 3/4. So that means that the slope of the function at x equals 4 is 3/4. Now let's do the same over here to the left with 9. So all we have to do is just plug in 9, and we're going to get 3 over 2 times the square root of 9, and this is going to be 3 over 6, which is going to be 1/2. Okay, so let's get rid of this and let's do part B. So for B, we have that f of x is equal to x to the 4 over 4 minus 3 x cubed over 2 minus 2x squared plus 15x over 2 plus 3/4. So notice that what we have to do really is just apply the power rule to each and every one of these individual terms, right? So the derivative of this function would be equal to 4x cubed over 4 minus 9x squared over 2 minus 4x plus 15/2 plus 0. Notice that here the derivative would be, the exponent is 1, so the derivative would be multiply by 1 and then subtract 1 from 1, that's x to the 0, so basically it becomes just 15/2, or whatever whenever you have an x and you do x to the power of 1 and you do the derivative of that, it's going to be the coefficient basically. So let's simplify this a little bit. We see that 4 over 4 cancels out. So this is the derivative, and they want us to find the slopes at 5, 243 and at 0, 0. I'm going to do 0, 0 because it's easier. And notice that 0, 0, just plug in 0 and we're going to get 15/2. Now over here, let's do the other one for 5. So for 5, we have to plug in 5 just like we would do in a normal function, right? So this would be 5 cubed minus 9 times 5 squared over 2 minus 4 times 5 plus 15/2. And if we do the mental math here, this is going to give us 0, which means that at x equals 5, this graph has a maximum or a minimum, or the slope is 0. You know what it means that at x equals 5, you have something like this, and you have just a slope that is a horizontal line. Okay, so here we are now on example 12.9, and it says the curve y equals ax cubed plus 7x squared minus 8x minus 5, a polynomial, has a turning point at the point where x equals negative 2. Determine the value of a. Okay, so a here is a constant, right? It's the coefficient of x cubed. Now, one of the things that we have to understand here is what a turning point in a graph is. So if you have a function, and let's say it goes up like this and then it goes down, this is what's called a turning point right here. Now notice that when you have a turning point, the slope of the tangent is equal to 0. So that's a very important fact that will help us solve this. Notice that this would be another turning point here as well. So the first thing we should do then is find the derivative, because the derivative is what gives us the slopes of the tangent lines, right, at the given point. So the derivative of y would equal 3 times a x squared plus 7 times 2, 14x, minus 8. And then the minus 5 would just be 0, right? So the derivative of a constant is 0. So this is the expression. So they're telling us that at x equals minus 2, so at x equals minus 2, the slope is 0. So we can plug those two values in here, right? So the slope is 0 when x equals 2, or negative 2. So negative 2 squared plus 14 times negative 2 minus 8. And now we just solve for a. So let's do the math here really quick. So this would be 8 is equal to 4 times 3, 12a, minus 14 times 2, that would be 28. And then we send that to the side, so this would be 36. 36 equals 12a. Therefore, a equals 3. Okay, so here we are on example 12.10. And it says boiling water is poured into a cup. The temperature of the water in degrees Celsius, C, after t minutes is given by this function for t greater than or equal to 1 minute. Okay. Find the average rate of change of the temperature from t equals 2 to t equals 6. So that's question A, where they just want us to find the average rate of change. So the average rate of change really is using the slope formula to find the slope of the line that goes through those 2 points, right? Because where t equals 2, let's plug this in the function, and we're going to get that the temperature is going to be approximately 83.35 degrees Celsius at that point. And at t equals 4, plug that into the function, we're going to get that the temperature is approximately equal to 31.38 degrees. So you can see the temperature is dropping. Therefore, the average rate of change would then be difference in y over difference in x. So 31.38 minus 83.35 divided by 4 minus 2. And this is going to give us about negative 12.99. So the answer would be that the average rate of change of the temperature from t equals 2 to t equals 6 would be then, we need to write this in 3 significant figures, so that would be minus 13.0 degrees Celsius. So the temperature is dropping at an average of 13 degrees Celsius. So that would be A. So let's focus on B. So let's get rid of this for B now. In B, they ask us to find the rate of change at the instant when t equals 4. So whenever they say instantaneous rate of change, that implies that we're going to need a derivative. So we need to find the derivative of the function. So if c equals 19 plus 182, and I'm going to rewrite t as t to the power of negative 3/2. Negative 3/2. Okay, so the derivative of this, so the derivative of the temperature function in terms of its time would be then equal to, well, this would just be 0, right, because the derivative of that is 0. And this would be negative 3/2 times 182, and t to the power of this minus 1, so that would be negative 5/2. Negative 5/2. And then we can rewrite this, we can simplify this, right, because this would be the same as 91. 91. And we can rewrite this whole thing just to make it simpler as negative 3 times 91 would be negative 273. No, negative 273. And let's write this as t over t to the 5 halves, which is the same as the square root of t to the 5. T to the 5. So this would be, we can simplify this further, but I'll just leave it like that. This is going to be the derivative, and this is going to give us the instantaneous rate of change. So then all we have to do is find out what the instantaneous rate of change is at t equals 4. And for that, we just have to plug in 4 into the function. So this is going to be negative 273 divided by the square root of 4 to the 5, 4 to the 5, and that is going to give us negative 273 over 32, and then plugging that in the calculator is going to give us approximately negative 8 point, say 53 degrees Celsius. So this would be the instantaneous rate of change at t equals 4. Okay, so now we are on example 12.11, and it says differentiate from first principles. So whenever they say first principles, it means use the definition of derivative that Fermat came up with. And A, find the derivative basically of sine of x. I'm going to do A in the video, and you guys can do B later on because the procedure is pretty similar. So, because we're talking about first principles, we need to use the definition. So limit as h approaches 0 of f of x plus h minus f of x over h. So in the case of sine, we can write this as limit as h approaches 0 of sine of x plus h minus sine of x over h. So now the question is how to expand this, right? This expression here, if you look at it, sine of x plus h, we can apply the angle sum identity. So let's rewrite this as limit as h approaches 0 of sine of x cosine of h plus cosine of x sine of h. And then let's not forget minus sine of x and all of this over h. Okay, so the next question is now what? Very well. So remember that previously we saw a couple of identities that I said, or a couple of limits actually, that I said were very important. And those were the following. The limit as x approaches 0 for sine of x over x. Remember that equals 1. And the other important limit is the limit as x approaches 0 for cosine of x minus 1 over x, and remember that this one equals 0. So we can use these two principles in order to simplify this expression by manipulating or doing some algebraic rearrangement here. So let's try to do that. Let's move this over here, and that would leave us with an expression that looks like this. So it would be the limit as h approaches 0 of sine of x cosine of h minus sine of x. And I'm going to divide this up. So this would be over h plus the limit as h approaches 0 of what we're left with, right? So that would be cosine of x sine of h over h. over h. Okay, so this would then equal the limit as h approaches 0, and I'm going to factor out sine of x. Sine of x times cosine of h minus 1 over h plus, I forgot the 0 back here, okay, plus the limit as h approaches 0 of cosine of x times sine of h over h. So I'm separating them on purpose so we can see something, because now we can apply the properties that I just wrote above. So notice that this expression here, because we're doing the limit as h approaches 0, and then sine of x acts like a constant because it has nothing to do with h, then this would equal 0, all right? Therefore, this expression equals 0. So we have 0 plus, and let's look at this other side. Remember that sine of x over x is 1 when x tends to 0. Well, here we have the same situation, but with h, right? So this is equal to 1. So this expression would just be equal to cosine of x times 1. So this would be equal to cosine of x. Therefore, we have the final outcome, and that is that the derivative of sine of x is cosine of x. Okay, so you're left with part B, and in part B, you should find that the derivative of cosine is negative sine of x. And this is going to be the last part of the video. After this example, you're going to find 15 exercises at the end of this section of chapter 12, and I would recommend you guys do them. I'm sending you an updated version of the PowerPoint that includes those questions from the practice plus their answers.